All right, so thanks for tuning in again, whoever is tuning in out there. Um, this video may be one of the longer ones, and it's going to be a whirlwind sort of tour through some of the important concepts I think that you need to understand, at least at this very basic level, for the immunology and the virology side of things to make sense. And so I'm going to attempt to distill down 4 years of my undergraduate studying into a few slides, and hopefully this makes sense to the majority of the people out there. It's not inclusive, like all inclusive. There's a lot of information missing here, but I think some of this is maybe the more important things that that come up in virology, and you would need to kind of just wrap your head around to make sense of, when somebody says something about a viral protein, it isn't just some magical process. You can think through how that viral protein came to be. And so I'm hoping that this and then the next video on transcription and translation can sort of do that. And after that, we can move into immunology. And so the overview of the topics that I'm going to cover here, in the physics category, we're going to talk a little bit about the forces that are involved, intermolecular forces, hemodynamic properties of blood, osmosis. In the chemistry side of things, just sort of reviewing what elements are and the organic elements and how those are important to life, a quick review of structures of atoms, and then maybe a slide here about acid-base chemistry, and then the biochemistry side of things, which is maybe the most important, and just to understanding biology, I guess. Structure of DNA, a little more in depth. I touched on it before, but talking about nucleotides, and then getting into the proteins and amino acids and proteins. And so starting off with electrostatic forces, just as a caveat, I did terrible in physics, so you don't need to be a genius to get this. I really struggled with it, but at least this part of it made sense to me. And so we all maybe can just intuitively think back to when you play with a magnet that you have a positive and a negative charge there. And we think of this as opposite charges which attract, and like charges, whether those are two positives or two negatives, will repel. And so this comes up in biology, and especially in virology when you're talking about receptors and spike proteins that a virus has. A lot of those proteins are charged on their side groups, their amino acid side groups, which I'll cover in just a little bit here. But it sort of starts to make intuitive sense then why a spike protein of one charge will interact and lock in tightly and nicely with a receptor of the opposite charge. And so just to review what that looks like here, we have two opposite charges, and the force of particle A over here, this charged particle, exerts an attractive force of this particle towards this way, and the same is true of the opposite. This force exerted by this charged particle is in this direction towards it. And so talking about the same charges, like charges, we have this particle, this charged particle, and exerting a force away from it on this same charged particle. So the same charges repel, and conversely, the force of this particle on this one is in this direction. And so that's just really more the definition. Really, if you just stick to opposite charges attract and like charges repel, that should get you a long way at least. So hemodynamics, this is important for, especially in immunology, in blood flow. And so one of the ways that cells get into the tissues, underlying tissues that they need to be at, is by regulating the capillary beds and the blood vessels. And so this equation, again from physics, explains why that works. And I just thought it's, I don't know, when things make sense and you can see them, I'm really happy when that happens. And so just quickly, what this shows here is that the area of the initial area times the initial velocity has to equal the final area times the final velocity. So if we were to just plug in some numbers, this isn't going to be heavy math or anything. It's just an example. Oh, this kind of cut off here, but if you were to take a 2 micrometer or oops, what did I do here? Yeah, so we have a 2 micron area, 2 microns squared, times 2 microns per second velocity. Then the other side of that equation, let's assume that the area is getting larger, as is the case when you have an inflammatory response. You have this vasodilation because of these inflammatory mediators. It will open up blood vessels. So we're going from a small area to a larger area. And then we can ask ourselves, what happens to that blood flow? And so if you were to just solve for that second velocity, we see that it is now a smaller or a lower number. So we went from an initial velocity of 2 microns per second to 0.4 microns per second. And so that makes it, and I think it makes total sense. You took a blood vessel, which was somewhat constricted or just normal baseline, and you increase that overall area diameter of it. What's going to happen to the blood flow? It's going to slow down, and that really explains why leukocytes are able to extravasate and move into tissues. And so if those words don't make sense to you right now, just hang on to them for future lectures. This is just to demonstrate to you that we know that this occurs, this property of leukocytes moving into tissues, in part due to just physics. So it's really kind of nice when something like that works out. And so osmosis and oncotic pressure are 2 important concepts. When we talk about osmosis, we're talking about water moving across a semi-permeable membrane. And so here's an example where you have the same amount of liquid on both sides, and you've got a lot of particles. We'll just call them particles. It could be anything. In this case, you're calling them sugar. And less concentrated on this side. And so what this image is trying to demonstrate to you is that water is going to flow into the area of higher concentrations of particles. And it does that so that it can equalize and come to an equilibrium. And so it doesn't make total intuitive sense at first. It took me a long time to wrap my head around this. But yeah, if you have a ton of sugar or a ton of salt, and on one side, water is going to move towards that side, and it will actually offset it like this. And that's at equilibrium in this case. And so this is important when talking about things like blood flow and edema. And so on the right is my drawing that I made of a blood vessel. And so in here, this cutaway is supposed to be inside the blood vessel. And these are, I don't know, erythrocytes. And you can imagine some platelets in there. And albumin is another really abundant protein. It's actually the most abundant protein. And so albumin serves this role in stabilizing this oncotic pressure. So your heart beats, and from there you have this really forceful flow of blood moving through these, moving through the arteries and into the arterioles and down into the capillary beds. And that puts a lot of strain on these vessels. And so you have this strong hydrostatic hydrostatic pressure pushing against the vessels, the walls of these blood vessels. The counteracting force to that then is the colloid oncotic pressure. And so that is all of these proteins, which I mentioned in here. I mean, you've got blood erythrocytes, but you do have, like I mentioned, the other proteins that are in the blood, which I've mentioned here. They're in here and they're drawing water in from the tissue. And so it sort of resembles what's going on here. You have more solutes inside the blood vessel. And while this hydrostatic pressure is forcing that water out, all of the concentrated protein in here is drawing that water back in. And so that's really important in immunology and understanding why you have edema fluid building up. If you have inflammation and it causes these blood vessels to become leaky, you're going to lose that albumin protein into the surrounding tissues, and now water is going to follow that instead of staying in the blood vessels. Again, another one of those examples where it makes total sense. So just a really brief review of the periodic table of elements and what this is. It's a really elegant system. I don't know how these people came up with this so many years ago without having the molecular tools and the atomic tools we have today. But this is a multi-layered, organized table. You can search videos on that for yourself, but there's a lot of information here, and the way it's laid out tells you a lot about these elements. But what are these? They're pure substances of only one type of atom present. So when we're talking about carbon, we're talking about only carbon atoms. There's nothing else in that. Whereas something like a sugar molecule has carbon, it has oxygen in it, and it has hydrogens. So this is the basic, the fundamental substance that we're talking about. In life, we deal with these organic elements, and so some of these would be like carbon, nitrogen, oxygen, fluorine, hydrogen. These are elements that show up abundantly in life, and so you might hear them referred to as organic elements. The atoms, which these are, which consists of these, are made up of protons, which are your positively charged particle. You have your neutrons, which don't carry a charge, and then you have the electrons, which balance the protons charge. And so the electrons are on the outside, whereas the protons and neutrons are in the nucleus. And so the electrons are actually maybe, I don't know about the most important, but they're what make chemistry occur. The transfer of electrons is chemistry, and that ability to share or steal or give up electrons is what makes things reactive. And I think one of the points I want to make here is that just because something, an element on this table is in something, doesn't mean it's a bad thing. And I've mentioned that before with an example of lead, but I'll mention another example here with sodium chloride or table salt. So sodium by itself will react with water, and it is explosive. It will blow up. It's dangerous to handle, highly reactive. Chlorine is, it can be toxic. It was used during World War I for, gas to kill people. But when you combine the two, you come up with this inert substance known as table salt, and we can eat it and consume it, and it does absolutely nothing to us in moderation. And so the point I'm trying to make here is that you sometimes hear, especially in nutritional sciences, people talking about something might have fluoride in it, or I don't know, anything, pick any, copper in it, or they might sell you a product because they said it has silver in it. That only matters in a given situation. Just because it has silver in it doesn't mean it has antimicrobial properties. It might not be in a place that silver can even interact with a microbe, or it has no way that the microbe would ever take it up. Rubbing a bar of silver on a microbe probably won't do anything. So that's something to think about. And this is where you can start, you learn these things and you can start questioning people on some of the bogus things that they're trying to sell you on. So yeah, that's that. So here's another one, acid-base chemistry. People will try to sell you pH balanced water, which is the biggest scam and bogus thing on earth. So what is pH? Simply put, it's the concentration of free hydrogen, or these H protons, H plus protons, so they're hydrogens without an electron, and it's the concentration of those within a given solution. So mathematically, we can express this as the negative log of the concentration of hydrogen equals the pH. And so if I were to tell you that the pH of something is 7, I can then measure using algebra what the concentration of free hydrogens are. In this case, 1 times 10 to the negative 7th. And so this is just a useful tool for sort of gauging how acidic or how basic something is. The scale moves on a scale from 0 to 14, 0 being the most acidic. Maybe it's 1, actually. I don't know if 0 is part of the scale. We'll say 1, because that's what's listed here. 1 to 14 then. 1 being more acidic, 14 being more basic. Both of them can be harmful. Just because something's basic at a 14 doesn't mean it wouldn't hurt you. It would melt your skin, just like something at a acidity of 1. 7 is neutral, and 7.4 roughly is what we consider physiological pH. So when you consume anything, it doesn't matter if it's, people sell pH balanced water, as I said, and that makes no sense at all, because if your body couldn't handle slight differences from what it's used to, 7.4 pH, then drinking something like lemon juice, I don't know, would kill you, right? So this idea that you need to drink pH balanced water or it's better for you is totally bogus. It doesn't matter, not one bit. And what's even funnier is people like Gwyneth Paltrow, who say that they like to have their pH balanced water with a spritz of lemon juice. Well, what happens when you add lemon juice? You make it more acidic, so you don't have pH balanced water anymore. It just doesn't make any sense at all. Don't buy into it. It's bogus. So anyway, the Bronsted-Lowry definition of an acid base here is acids donate protons, whereas bases accept protons. And just a short example of what that looks like. I don't know why the A popped up down here, but you have some acid and it interacts with water, and you wind up getting a transfer of that hydrogen from that acid. It donates that proton because it is an acid, and the water accepts that hydrogen because it is acting as a base in this case. And so you wind up with a transfer of that proton. And so this is really important in immunology and virology, but just an example of where these things matter. Cells will take up viruses into their endosomal compartments, and they will basically try to kill them by acidifying them. They will pump hydrogen protons into the endosome and hope to denature the envelope or the capsid of the virus. pH changes can be detrimental to a virus, so that is one way to kill a virus, or degrade a virus might be a better way of putting it. All right, so more on DNA. So there's DNA stands for deoxyribonucleic acid, and we also have RNA, which is ribonucleic acid. And so I touched on this before, but a couple properties about DNA. It is a double-stranded helix. It is polar in that it orients itself in 2 different ways in opposite directions. So we call that anti-parallel. And so what I mean by that is up here, we call this a 5' end right here. And so the opposing side at that same end would be the 3' because it's running anti-parallel. So 5' here runs to 3'. On the opposite side, if you were to think about that in the opposite direction, 5' then is at the bottom, and it runs to the other way. It runs to the top with 3' being at the top. This is important if you were to want to understand more about DNA synthesis, which I'll cover a little bit in transcription, but I won't get into the major details. But it is something that you should maybe be aware of. This is how DNA complementary base pairs. So we've got G and C and T and A. These are the 4 bases, which I've mentioned in previous videos. And so these are always complement to each other. And if they're not, that means there's a mutation or some sort of substitution that's occurred. And so when you look at DNA, you should expect to see G base pairing to C and T base pairing to A, and that the helix runs in this anti-parallel fashion, 5' to 3', and then on the opposite side at the bottom, 5' to 3'. So what did I say here? So all life on planet Earth does contain DNA. There's no other storage material that cellular life uses. The only exception to that then are viruses, which can be composed of DNA or RNA, but never both, not that we've discovered yet. And so one of the reasons why this has evolved this way is because DNA is just inherently more stable. So if you think back to the couple slides before when I was talking about electrons, DNA and RNA look very similar. The difference being at this 2' carbon right here. And so we see that DNA does not have this OH, this hydroxyl group at the 2'. And so this is important because on this oxygen, there are 2 two lone pairs of electrons that are just hanging out there, but also this hydrogen can get stripped away pretty easily. And so what that means is this will actually react on itself with this 3' carbon over here. It'll transfer its electrons over and remove electrons and push them. And it's just really unstable. It doesn't last very long in the cell. And so life may have evolved with this first, or at least that's the belief, that RNA was the basis of life first, and then a sugar like this here was used instead, deoxyribo, meaning deoxygenated ribose, the sugar, ribose, and this is much more stable. DNA can persist in the environment for hundreds to, thousands of years. That's why we can do radiocarbon dating and other techniques like that on mummies and stuff like that. So again, this is where you don't need to take my word for it that DNA is more stable. You can use the information I've given you about chemistry and say, okay, so I know that oxygen has these electrons and it's highly unstable in this orientation. And because of that, again, it makes total sense that DNA would have evolved to be the storage mechanism of our genetic material. All right, and so coming to just the last couple slides here, again, I know this is moving through things fast. If you can grasp any of this, though, it'll really make the actual immunology and virology stuff make sense. So this is maybe more of the important stuff too, understanding what amino acids and proteins are. So amino acids are what we call sort of the building blocks of proteins. And so this is just a generic amino acid. It's comprised of this amino end. It's got a central carbon, this alpha carbon with a side group. This can be a lot of different things, but these are like your tryptophans, your alanines, glycines, isoleucines. There's 20 or so, 20 amino acids, yeah. And then some other uncommon ones. And then this is the carboxy end of the amino acid. And so these get strung together and they make up what we call a protein. And the proteins do all of the work for the cell and viruses. And these are encoded by the genetics, the genes of whatever organism we're talking about. And it tells, those genes tell the machinery of the cell which amino acid of the 20 amino acids to place next. And so this can be really important in that if you switch just even one amino acid, you change the function of that protein. And so one example is sickle cell anemia. It is a single amino acid substitution. I don't remember what they were. I think it might be like a valine for an isoleucine or something. But at any rate, you're changing only one single amino acid, and now you wind up with a disease that unfortunately can kill you later in life, and it causes problems throughout life due to a lack of oxygen transport. So to put this in a bigger perspective, the amino acids, I said, are strung together, and we get this secondary structure like this here. So the primary structure is just amino acids strung together. The secondary structure are these interactions that the R groups, the hydrogen bonding that can occur here between the different amino acids. And so you get these helices, which are important for many viruses. They have structures like these. And then you get into these bigger tertiary groups or tertiary structures where the R groups, side chains, start to interact. And this can be through electrostatic interactions, so positive and negative charges being attracted or repelled, and that plays a big part in the way viruses interact with host cells. And then when these structures, which we could call this a protein at this point, well, we would call it peptide, I guess, because it's not fully functional yet. This is a peptide in this case. And then when 4 of these peptides get together, we get this, what we call a quaternary structure. And this is the complete protein, the protein being defined as a fully functional component that carries out some job in the cell. And so that's actually hemoglobin. And right in the middle pocket here is these little heme groups where oxygen would bind to. And if you were to look at the charge on that, you would see that the heme carries a positive charge and oxygen carries a negative charge. And so again, it makes total sense why oxygen binds to this, thinking back to what I've talked about with chemistry. And so, yeah, I think these concepts aren't just, for pedantic talk. It's to actually understand why this stuff works the way it does. All right, and so the last slide here then, I think, was I wanted to just talk on what enzymes and metabolism is. And so enzymes are these proteins, so we know what a protein is now, and they are made by the cell, and they carry out jobs that really facilitate chemistry within the cell at a reasonable rate. The chemical reaction of a piece, like a molecule of glucose being broken down, is the very same combustion reaction as if you were to light a piece of wood on fire with a stick of dynamite. That explosive hydrocarbon with oxygen leading to a release of carbon dioxide and water. That is the same exact reaction. Obviously, we don't explode when we eat glucose, though, and that's because it's released slowly. And when we need things to be sped up, though, we have enzymes. And so the enzyme will take a substrate, it'll bind it into its active site, and it sort of it does its chemistry right here. It does whatever it needs to here and releases them. And now those have been acted upon, and it might change the property of them in some way. And so this is important in metabolism. And just briefly what metabolism is, I guess you can call it this process of building up or breaking down biomolecules. And it really is the processes of life. So you'll hear probably a lot about metabolism when you talk about virology. And the other important note here is that enzymes are highly specific for performing their activity. And as I mentioned, they reduce the time, and really it's the energy that they're reducing. So an uncatalyzed, we call it a catalyzed reaction if an enzyme's involved. And so we're starting with our reactants here. And in an uncatalyzed reaction, it takes a lot, we'll say all this energy for that reaction to take place to get your final product. However, if you add an enzyme, it lowers that activation energy, and you can get over that barrier with less energy and quicker, typically. And so that's why that's important. All right, so I know it was a lot, and it was probably fast and a whirlwind of information, but it's really necessary, and it's not just for just to talk about it. It is really important to understand some of these other concepts. And again, that was, we're talking 4 years of information distilled down into and glossed over into just a few slides. So there's a lot missing there. But in the next video, I want to do that transcription and translation, which I talked about, and then DNA synthesis. So I will go ahead and make that and look forward to putting that up. Thanks for listening.